of g of x is positive for all data points. So for that, what we will do is we'll start with some random. So finding g of x means finding w and w naught. So w is a vector, w naught is a scalar, right? Finding these two things. So how do you do that? We will define some kind of a cost function called capital L, because in all these techniques we are so used to defining some kind of a cost function, right? So we want dj times g of x. Okay, so we want dj times g of xj to be greater than 0 for all xj. So we'll define a cost function called dj times g of xj. Okay, if L is negative, right, that is uh, dj times g of xj is negative, right, that is dj times w transpose xj plus w naught. If this is negative, then something is wrong. So for that data point, the g of x is not correct. That means the weights are not correct. So now the question is correct weights, so that this problem goes away. That is, for that data point, this quantity is negative, so it should not happen. So correct W and W naught such that, right, the above inequality is corrected. Is corrected. Okay, so how do you do that? So let us do this. Now let us consider this kind of an update rule for W as, yeah, equal to some dj times xc. Okay, so eta is just a constant, some kind of a step size. I want delta W to be proportional to dj times xc. And typically this eta is a small positive number. Now what happens when you do that? What we will show is, so delta W t is basically W at t plus 1 minus W at t. You can take it as t plus 1, you can take it as t plus delta t, whatever it is. W is updated from one iteration next iteration. That the update should be proportional to dj times xj when this inequality is in occurs, right? When this violation of the correct condition is occurs, that you need to update the weights according to this rule. Okay, why is this, why is this equation correct? Right, why is this kind of update rule? Why is it correct? Let us see that. So let us consider, right? So we said W t plus 1 is equal to W t plus eta times dj xj. So L of t plus 1 is equal to dj times W transpose t plus 1 times xj plus W naught, because when you're looking at the updated value of L, the update is occurring only because of update in W. So only W of t plus 1 occurs on the right side. So similarly, if you take L of t is equal to dj times W transpose t times xj plus W naught. So therefore, if you take L of t plus 1 minus L of t, and if you subtract these two, this dj W naught gets cancelled in both. So you get dj times W transpose t plus 1 minus W transpose t times xj. Okay, so that will be equal to dj times. So this difference we have seen, right, is equal to this eta times dj times xj. So dj, so there's a transpose here sitting. So DJ is scalar, so transport doesn't affect it. Transpose doesn't affect it. We get this. So that is equal to eta times dj square times xj transpose xj. So you can easily see that this whole thing is greater than 0. Okay, what does that mean? What that means is L p plus 1 is greater than LT. Okay, so because of this update rule, so right now, so what we have done is when L is less than 0, and we use delta W is equal to eta times uh, sorry dj times xj, then the update that you get LT plus 1 is greater than LT. So what means, so whenever L is less than 0, we update like this, L is increasing. So then L is going towards a positive value, so which is what we want, right? So that is one good. So this is how, so changing W according to that previous rule is correct. What about changing W naught? Okay, how do you change this? So the answer for this is change W naught as eta times just dg. So whenever L is, if L is negative, right, L should be positive. So if L is negative, update W naught like this. And why is it correct? Let us see that again. Now L of t plus 1 is equal to dj times W transpose xj. So now there is no update in W, so we keep it like that. Plus W naught t plus 1, only W naught is updated. So L of t is equal to dj times W naught xj plus W naught t. So therefore, L of t plus 1 minus L of t. So the first term gets cancelled, is equal to dj times W naught t plus 1 minus W naught t. Right. So this update, this is delta W naught, that is equal to dj times eta dj. So that is, we are using this equation here. So which is equal to eta times dj square, which is greater than 0. So here also, so if you update W and W naught using the rule here, right, and the rule here, and that will tend to increase L. So obviously you have to do this update only when L is negative. When L is negative, if you apply this, this increases. Right, so if you keep on doing it for all the cases where the L is violated, this inequality is violated, the equation inequality is violated, then L keeps on increasing until it becomes positive. So this is the idea, right? So this is this is a learning rule, right, for this linear discriminant function, where delta W is eta dj xj and delta W naught is just eta dj. Right. So thing is everything okay with this, or you think there is any problem? Any comments on this? Hello. So we have some data here. So, hey, just 1 second. I have somebody at the door. Just 1 second. Hello, sorry about that. So you have
Okay.
one data set C1 like this, another data set C2 like this. Right? I'm trying to discover the correct separate relation surface. So suppose, so what is happening in this previous algorithm? Suppose my initial g of x equal to 0 line, if it is like this, right? So my w is wrong, w naught is wrong. As you keep on applying these two learning rules, right? What will happen is this line will gradually turn in small steps, and finally, once it reaches something like this, at this point, um, the the L will be positive for all the data points. So then the iteration will stop. So you have found the correct answer. But do you think there's any problem with this? It looks very nice theoretically, but anybody does it? Do you think any problem with this? Hello. So let us take the point C1 like this. So C1 data is like this, and C2 data is, let's say, like this. So now I'm trying to separate this using a straight line, right? So obviously it's not possible. Whichever way you draw the line, right? You'll have points from both classes sitting on the same side of the line, no matter how you draw the line. So in this data set, you cannot separate the two classes by drawing a line or by using a hyperplane, right? Because you need a complicated surface, not a plane, not a straight line, but a curve to separate these two classes like that, right? So in this case, you are trying to separate classes using only a straight line in case of 2D or using a hyperplane in case of multi-dimensions. So you may not always be able to do that. So there's a serious limitation to linear discriminant function, right, based classifiers, which is that it can classify only linearly separable data, right? So if the data can be separated by a line, only then, sorry, this is supposed to be a line. So only then this algorithm can discover that line, otherwise it will fail to discover that line. So linear discriminant based classifier is okay for starters because it's a simple theory that we can understand. But in practice, you need something nonlinear. So for that, we will use something slightly more complicated than this. We'll introduce neural networks, and then we'll slowly go to, first we'll start with a very simple neural network. Because the moment you talk about neural networks, you are talking about nonlinearity, right? Linear discriminant function is only a first step, which is linear, right, by definition. So let us start looking at neural networks. Let's start with a very simple one. They're nonlinear. Let us see if they can overcome the problem we just faced with linear discriminant functions. So we'll define first what is called a neuron. Actually, we'll define a simple kind of a neuron model. Let's not get into the biological aspects because it's not a biology course or this is not a neuroscience course. But we'll define something called the McCullough and Pitts neuron model, which is proposed by two guys called McCullough and Pitts. And this neuron model basically takes inputs from a bunch of other neurons and produces an output. The inputs are x1, x2, x3. These are real numbers. So x is so xi is basically a real number, and output y is also a real number. And if you look at vector x, that's an n-dimensional vector. So all these inputs are combined in the neuron, and then it performs a nonlinear function operation on top of this, and produces an output. So so that combination is done by this expression. Okay, so sigma wi xi minus b. So what is going on here? the combination is done through certain weights, because you're not just adding up all the inputs, you are weighting them using certain parameters called weights. And if that total weighted sum, if it is greater than a threshold value called B or a bias value B, then the output Y is 1, otherwise output Y is 0. Okay, so this quantity, call this H, is equal to sigma Wi xi minus B. Okay, so our right sum of goes to 1 to n. If H is positive, Y is 1, okay, or maybe greater than equal to 0, Y is 1, else Y is 0. Right, so that's what the neuron is doing. So that all this has some biological motivation from the real properties of a neuron, but let's not worry about that. Now, for you to have this kind of a function, like what kind of function gives you this property? If the argument is positive, output is 1, argument is negative, output is 0. So that we are denoting it using a function called G. What function is G? Anybody?
Activation function.
Sorry, no. Mathematically, activation function is biology, but mathematical. This is a mathematical function.
Function.
Huh?
Function.
What function?
Step.
Step function. Yes, it's a step function. Okay, so g of h is step function. If the argument is positive, output is 1, otherwise it is 0. Later on, I'll talk about slightly. So this is sigmoid function, which is a variation of this, where it's not a step but a smooth version of it. We'll see that later. Why you need this and all that. So this is a basic neuron model, right? Which is also called the McCullough-Pitts neuron model. So this neuron stays in two states: up state or a down state, or active state or resting state. And active state is 1, or excited state is 1, and the resting state is 0. Sorry, this is 1, this is 0. Okay. So originally McCullough-Pitts proposed this neuron model as obviously as a model of the real neuron in the brain, right? And they wanted to understand using such models how brain computes, how brain works. And this was in the early 1940s, in the last century, when World War was going on, Second World War was going on. So at that time, they were using large computers, like for example, ENIAC computer in US was being used to crack the secret codes and all that. So it was just at that time, for the first time, people are seeing the power of computing, right, in action in the real world, in a very big way, in a very dramatic way. So it's natural to think of brain also as a computer, because it's a kind of caught the public imagination. So if brain is a computer, then neurons should be probably behaving like logic gates, because the logic gates and Boolean circuits, these are all the functional units of a computer, of a computing system, mathematically speaking. So these guys wanted to show how a given neuron can be shown to perform some basic logic gates, or logical operations. So we know that there are three fundamental logic gates: AND gate, OR gate, and NOT gate. Can we show that a neuron, the same McCullough-Pitts neuron, can implement these three logic gates? It turns out it's very easy. You can show that very easily. So if you take OR gate, right, the truth table, if you remember this research system stuff from your first year, the truth table for OR gate is like this: 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 0. So even if one of the inputs is 1, output is 1. So that can be obtained. So here actually we use the notation sigma, but we can also use the notation G. We use notation G for this function here, which represents step function. You can see that this equation now satisfies this truth table, because even if one of x1 and x2 is 1, the argument of this function is positive, so output becomes 1. Now in case of AND gate, truth table is 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1, which means only if both the inputs are 1s, the output becomes 1. So, and that can happen only with this, when this bias term is sufficiently high. In this case, bias term is small, that even if one of them is one, inputs is once, the argument became positive. In this case, bias should be sufficiently high, so that only when both are ones, argument will become positive. So we have chosen 1.5. We could have chosen any value between, slightly greater than 1 and slightly less than 2 would work. Here also in the previous case, any number, any bias term slightly greater than 0 and slightly less than 1 should have worked. So this will satisfy the AND gate truth table. In case of the NOT gate, it's very simple. It's a G of minus X plus 0.5, or any value between slightly greater than 0 and slightly less than 1 would have worked. All right. So like that, you can very quite trivially show how this McCullough-Pitts neuron model can be made to implement logic gates. So from then they kind of extrapolated these ideas and proposed that brain is a big Boolean circuit. It's like a logical machine, just like a computer. But point is, the first step is okay. I mean, you can think of neuron as a logic gate, but it's untenable to think of brain as a work like a computer. There are a lot of fundamental differences. If that one analogy alone, if you leave it aside, there are a lot of other differences between brain and computer. Because computer is, first of all, as a piece of matter, it's quite hard and it's made of 2D sheets of matter. Look at the chips, the printed circuit boards and all that, whereas brain is a soft tissue and it's a 3D tissue. Computer is mostly 2D, right? And it's powered by DC mains, and brain is powered by ATP. The signals goes from like a 5 volts or whatever. There's some standard voltage. We call it VCC, right? All the digital signals that operate between some VCC to 0 or VCC between minus VCC. Whereas in the brain, the signals are not. So if you look at the signals in the computer, they look something like this. Whereas in the brain, they don't look like this. They look like that. And also they don't come in the same frequency. They have all sorts of frequencies. Right, and this is a bunch of pulses with variable frequency. Another thing is extremely sensitive to faults. That's what a computer is. If you shake it a little bit, bang it a little bit, it's gone. Whereas brain, you would have banged your head on the wall very often when you're very frustrated. Still, I'm sure you're okay, right? Now the clock speeds are very high in a computer. That's where brain is quite slow. So computer clock speeds go into nanoseconds, right? Gigahertz and all that. Whereas brain is very slow. You only have 100 to 200 hertz is the highest. Now there is a centralized clock in the computer where everything rides on that clock, whereas in the brain there is no centralized clock. Right? All neurons have their own local frequency and they somehow coordinate their function. So that way it is very different. So although the computer clock speeds are high and brain clock speeds are low, brain makes up for it by using a very large network. So in the computer, number of processors, you might have heard of maybe a few hundred, a few thousand processors. But comparatively in the brain, it has about 100 billion neurons. So that where it becomes very powerful. Now power dissipation, 10 power minus 5 watts, so this is at, I think, single transistor level. Whereas in the brain, it is 10 power minus 10 watts. These numbers are not quite accurate, a bit old. I need to look up more recent numbers. But anyway, it is known that at single unit level, the brain is very energy efficient, much more energy efficient than a circuit in a basic circuit in a computer. Okay, so you need to think about the neuron model in a different way. It cannot be working like a logic gate. So that new thinking has come in the 60s with this guy called Rosenblatt, who said you don't have to prefix the weights of a neuron. So because in the previous case, when you wanted to make the neuron behave like a logic gate, you just hand-coded the weights of the neuron to make it look like a logic gate. Whereas the main thing, difference or special feature of the brain is it can learn from experience, right? You present some data over and over again, and brain learns that function. So similarly, he said you can train a neuron to make it classify patterns, just like we learned how to classify a linear discriminant function to make it classify some simple kinds of data. Right here also, Rosenblatt has shown that you can classify a neuron or a bunch of neurons to classify a set of patterns or classes. So how do you do that? So this is the picture is slightly messy. But let us say I have a bunch of neurons, and each these are inputs, and each of these inputs feeds into a neuron. So this is one McClellan fits neuron, okay, and so these are the n inputs, and this is, I'll call this y1, and these are x1, x2, etc., xn, right? And similarly, I can have more neurons. Okay, so I'll call this yi or yj, etc., etc., and then ym, right? So something like that. So this kind of a network can be trained to classify patterns. So how do you do that? So here is a simple schematic. I hope you can see it. It's a bit faint. The whole idea here is I have initially a neural network, this kind of a network, right? And now there are all these weights here. Now, since there are multiple neurons, the weights will be a weight matrix. So input is x and output is y. Uh, Now, if you have an n class problem or an m class problem, you need to have m outputs, right? And each class is defined by one neuron. So if it is class 1, the output must be 1000, etc. If it is class 2, the output must be 0100, etc. So that is how you code n classes or m classes in the output layer. So when you give an input, the network gets to give some output. Initially, the weights are random, so output is not likely to be correct. So you compare the output that you have actually obtained from the network with the desired output, and you will have some error. And this output is target output is T, or we also use notation D, which represents, right, T, which represents desired output, just different notation, means same thing. So you compare these two, and that difference error, right, is fed into the neural network. And using that error, I update all the weights inside neural network. So this arrow represents that the network, this module is adaptive. It is variable, right? So we do that, and then we can derive a learning rule. So how do we do that? So let us first do it for one neuron, right? So what we do is we train the network or change the weight so that the output y comes close to the input. The output, the actual output y comes close to the desired output d. Okay, which means you are trying to minimize a cost function defined by, okay, so I'll call this di minus yi over all the patterns. Okay, so actually, so di and yi are the ith output, right? These are the ith output. Okay, and so I have to minimize this over all the patterns. So how do you do that? So delta. So we know how to do gradient descent. We have seen it in some previous contexts, right? If I have a cost function, and if I have to minimize it, minimum is here, and if I am here, if the gradient is positive, I reduce the value. If the gradient is negative, I increase the value. So I have to move in the direction of, so delta W is proportional to minus of dou E by dou W. So this is what is called gradient descent. So how do we do that in this case? So delta Wi, um, okay, sorry. If I have only one neuron, so there's only one output neuron, so I don't need subscript here. I'll just have one Wi, which is equal to E minus of some eta times dou E by dou Wi. So that means pictorially, I have only one neuron. Output is Y. Input is x1, xj, xn. right? And so how do we do that? Means we differentiate this quantity. I get it's equal to minus eta r times d minus y times minus 1 times dou y by, sorry, dou w j. Okay, so actually half time, and you also have one more 2 here. So 2 and 2 gets cancelled. So you get minus eta d minus y minus 1 dou y by dou wj. So what is dou y by dou wj? So y is given as g of sigma wj xj minus b. So dou y by dou wj is equal to g prime. So this whole thing I'm defining it as h. Okay, and g prime times xj. So if you put this all together, you get delta wi. So this minus minus gets cancelled. You get eta times d minus y times g prime of h times x. If you do a similar derivation for the bias term b, right, you get delta b is equal to minus eta times d minus y times g prime of h. So actually what we got is, um, so you might have seen, notice some analogy between this and the, let me take one more page. Okay, so what we got is these two equations, the last ones. And hope you have noticed some analogy between these and the update rule for the linear discriminant functions. Okay, so g prime h xj and delta b is equal to minus eta b minus y g prime h. Whereas in case of linear discriminant function, we got delta w is equal to eta times. So this d minus y we don't have in case of linear discriminant function. But see, thing is, in case of linear discriminant function, we update the weight only when uh, the output is wrong, right? The point is classified wrongly. So here also, if d and y are the same, right, this term is 0, so there is no update. So only when d and y are not the same, it is an update. And when d and y are not the same, it means it could be either plus 1 or minus 1. So it will work out to be something like totally identical. So I don't want to do a detailed comparison, but you can take it as a homework. It will be like identical to what we have done in case of linear discriminant function. So this here we have xj. So this we do only for in case of wrong classification, right? So here we do this for all data, and when the classification is correct, that is when d is equal to y, then there is no update. So that becomes a special case. Whereas here we classify with this learning rule only when x is misclassified. Okay, so it will work out to be identical to the previous case. So you have xj times dj. Now in this case, you see there is a minus theta here. There is no there is plus theta here, and that is because in case of linear discriminant function, we had w transpose x plus w naught, whereas in case of this neuron, we had w transpose x minus b. So that is why there is a difference in sign here. Okay, so that so far so good, but this term g prime is slightly problematic. Okay, so and also g prime is slightly weird here because look at g function. If G is a step function, what is G prime? Anybody? Hello? If G is step function, what is G prime? The derivative of step function.
Delta function.
Very good. Yeah, so you have delta function. So if you plug in delta function here in this equation, what happens? Because delta function is non-zero and actually infinity at origin. It's zero everywhere. So that means for most h will be zero only very rarely. Otherwise, it will be some non-zero value between some positive or negative value. So mostly this will not work at all. Okay, so there is a slight problem with this. So this is not the correct derivation in case when G is a step function. So in practice, what we will do is we use G as we use a smoother version of use a smoother version of G, which looks something like this. So this is G of X. So this is called a sigmoid function. Okay, or more precisely, it's called a smooth sigmoid function. And when you have a function like step, this is called a hard limiting right function, where there's a discontinuity right at origin. In this case, this discontinuity is replaced by is removed by using a smooth function. When you do that, then what happens to G prime? And use smooth function like this. So far from the origin, this function will be flat, right? And therefore, that will be derivative will be zero. At the origin, there is a high derivative, and which is positive. So the G prime will look something like a bell curve. So one good example of a function which has this kind of features is what is called so this function is called a logistic function. Okay, this is an example. So when you use such a function, you get a smooth sigmoid function, and that will work. Okay, so this is how we train the perceptron, right? And so there is a different derivation for the perceptron learning, which is just like what we have done in case of the linear discriminant function, and that is what is called the perceptron learning rule, right? So we'll use that. Okay, so the learning rule is almost identical to the learning rule that we derived in case of linear discriminant function. So let us see how it works. Now let us apply this to again the simple OR gate. So this is a truth table for OR gate. In the previous approach, we just hand calculated the weights, and we have shown how you can train, you can make a neuron behave like an OR gate. But now what we'll do is we'll use this learning algorithm. Not this, but the perceptron learning rule is just delta wi equal to eta times d minus y times xi, or delta b is equal to minus eta d minus y. So this is closer to your linear discriminant function. You don't have this G prime problem, right? When you use step function, we'll use this. When you use a sigmoid function, we'll use that G prime. Because if you use in case of step function, if you use G prime, it will become useless. The weights will never change. Okay, so let us see the small demo, and we can stop here. So in case of OR gate, the 4 data points are here, right? You have one is here at 0, 0. Another is here at 0, 1. Then this is at 1, 0. This is at 1, 1. So there are only 4 points. The output is 1 at these 3 points, output is 0 at these 3 points, at this point. So the classification is, the ideal classification, right, should work something like this. That is, my decision surface should be like this, something like this, right? So initially I take some wrong weights. So weight W1 is this, W2 is this, and B is -2. For these weights, my decision surface is here, initial decision surface, which is wrong because all the points on one side of the line are positive. That means it is classifying all the 4 points as class 1, is giving output 1, so which is wrong for this point. So part presenting 0, 1 is correctly classified. So 0, 0 is wrongly classified. 0, 1 is correctly classified. 1, 0 is also correctly classified. 1, 1 is correctly classified. Out of 4, 1 is wrong. Okay, so it is 75% correct. So next time when I give 0, 0, so I've updated. So because Perceptron also, the weights are updated only when the output and the actual output and the desired output are different, when d minus y is non-zero. So when you update the weights using this learning rule, right, using this learning rule, this two, okay, the weights have changed. So second round, when I present the data point again, 0, 0 again, the weights are now like this. So you see that this is class 0, that is class corresponding to 0 output. This the classes data, this the correspond to the class correspond to the output 1, right? So these two are separated nicely by this line. So now this is a correct solution. So 0, 1 is also correctly classified, 1, 0 is also correctly classified, 1, 1 is also correctly classified. Now for this set of weights, right, the network is able to implement the OR gate perfectly. They got 100% complete this. The Perceptron learning rule also works, but the problem is, in this case also, the decision surface, if you look at this thing, decision surface is also a linear surface or a hyperplane, or in case of 2D, it's a straight line. Why is that? Because y can take only two values, 1 and 0, and the border between these two values occurs when the argument is 0. If the argument is positive, means output is 1, argument is negative, output is 0. So when an argument is 0, that's a straight line or a hyperplane. So therefore, this neuron also divides the input space into two semi-infinite halves. Okay, so it is not really giving us anything more than what we got from the linear discriminant function. So although we are using a nonlinear function g, in effect we are not getting anything nonlinear. We are not getting a nonlinear decision surface. Okay, so it is actually not very powerful, right? And so this also can only classify linearly separable data. And when that happens, one more property of this kind of a neuron model is, it can have, when the data is linearly separable, it can have infinite number of solutions. Because you see that here you have two classes, the green points and the blue points. I can separate these two classes using infinite number of straight lines, right? But when the data is not linearly separated, there is no solution at all. Okay, so if it's linearly separated, you can have infinite solutions. But if it is not linearly separated, there is no solution at all. So for example, if you take another logic gate called the Xor gate, where the truth table is given like this, right? For 0, 0 output is 0, 0, 1 output is 1, 1, 1 output is 0 again. For 1, 0 output is 1. That means these two blue points form one class and this green points form another class. So no matter how you draw the line, you will never be able to separate these two classes. So the perceptron won't be able to learn the Xor gate. It can learn AND gate, OR gate, and NOT gate, but cannot learn the Xor gate. So that became a big problem with the perceptron, and I'll skip all this stuff. These two guys, Minsky and Papert, who are like one of the pioneers in the artificial intelligence community, and which was just coming up in the 60s. These guys noticed that there is a problem with perceptron and wrote a very damaging commentary on perceptron, saying that it cannot even solve the Xor problem. So there is no point in studying multi-layer versions of a perceptron. Because in case of perceptron, there are just two layers, right? The input layer and the output layer. Okay, so input is given to the input layer, output is taken from the output layer. So this kind of a network is not able to classify, right, linearly non-separable, right, data. So they said there's no point studying more complicated versions of this network where you have more layers, right, between the input and the output. So this is the input layer, this output layer. In between, you can have more layers. Okay, so they just kind of made a brash judgment that there's no point studying multi-layer versions of this network, which will be called a multi-layer perceptron. So because of that, in the 70s, there was not much work done. But in the 80s, again, people forgot about all this criticism and started studying multi-layer versions of perceptron. And then suddenly they found that these models don't have all the problems of the perceptrons because they can classify linearly non-separable data also. So that has kickstarted a lot of research, and they were able to solve very difficult problems which were not solved by both the classical linear methods and also the obviously the linear perceptron, which is also effectively a linear machine. So in the 80s, several groups have discovered the learning rule for multi-layer perceptron and have shown that how it's a very powerful, right, method for classification. So let us discuss multi-layer perceptrons in the next class, which will be, I guess, not next week but the week after, right? So enjoy your vacation next week, and let us meet the week after.